Now we're going to look at what Newton's method says. Newton's method helps us find our roots, our zeros of our function. And so we might not be able to find that zero. It might be really hard to find that zero. So what you're going to do is you're going to make some estimated guess of where you think that zero is going to be. So let's say that you chose some estimated guess and you thought that it was crossing the x-axis at this value. So let's call this x of 1. So if we do that, we are going to look at the equation of the tangent line at x of 1. So if I went over here and up to x equals 1, and I thought of where my tangent line would be there. I don't like how thick that is. So at x equals 1, maybe. Let's do this again. Okay, it doesn't matter. It's going to stay thick, right? We get this value here. So if we looked at this and we found, go away. How do I get rid of that? If we went in here and we found where this tangent line was crossing the x-axis, notice that we're really close to R. So what we're going to do now is we're going to choose this value where our tangent line is crossing the x-axis as our next guess. So let's call that x of 2. So what we're going to do is we're going to go up here and we're going to find the equation of the tangent line at x of 2. So if we go up here and we find the equation of the tangent line when x equals 2, x of 2. Sorry, I'm trying to do this so that it's nice, but it's not doing it. Okay, so we get this over here. So notice that that estimate now got us even closer to where that 0 was, where it was crossing the x-axis. So you're going to even do this even further. You would choose this to be our x of 3 value. And you would then go up here and you would find that equation of the tangent line. And we'll keep on doing this. We're going to get closer and closer and get a great estimate of where that 0 is. Okay, so this is the reasoning behind Newton's method. So I pulled up the formula in order to find Newton's method. And basically we get this by using our linear approximation formula to find out where this is equal. So for instance, maybe let's just derive it. We know that L of x is equal to that f of x plus f prime of x all times, let's say this is x of 1, x minus x of 1. This is approximately what our f of x value is. F of x is what we're trying to find is when this is equal to 0. Anyways, it's not working out as how I want it, but this is how we're gonna get this formula by using that. So let's just apply the formula to find out our zeros. So let's say you're given And they actually call it x of 0, the first one they do. So this would have been x of 1, this would have been x of 2 if we call it 0. X of 0, given x of 0, we want to find x of 2. And we're given f of x is equal to x cubed minus 7x squared plus 8x minus 3, and at x of 0 is 5. Okay, so this is some guess of where this f of x is crossing the x-axis. So we can find where the tangent line is crossing the x-axis when x of 0 is 5. So we can find x of 1, our n value in our case is 0. X of 1 is equal to our x of 0 value minus f of x of 0 all over f prime of x of 0. Okay, so let's go in and figure out what our values are. Let's first of all figure out what our derivative is, because we're going to need this derivative function for this formula. So let's find the derivative of f of x. When we find the derivative, that gives us 3x squared minus 7, derivative of 7x squared is 14x, derivative of 8x, so plus 8, and derivative of a constant is 0. So we want to find out what is f of 5. If we go in there and we plug in 5 wherever we see an x, that would give me 5 cubed, or 125, minus 7 times 5 squared, which is 25, plus 8 times 5, so plus 40, minus 3. So this is 125 minus 7 times 25. That's 175. 40 minus 3, so that's plus 37. So this is 125 minus 175 is negative 50. Negative 50 plus 37 would be negative 13. If we look at the derivative, though, at 5, we're going to get 3 times 5 squared minus 14 times 5 plus 8. So we have 3 times 25, which is 75, minus 14 times 5, that's 70, plus 8. So 75 minus 70 is 5. 5 plus 8 is 13. So if we look at what x of 1 is, plugging it into this formula, this is equal to my x of 0 value, which was given to us. Sometimes you might have to make that choice yourself, 5, minus f of x, f of 5, which we found to be negative 13, all over the derivative at 5, which we found to be positive 13. So really that's 5 plus 1, which is 6. It wants us to find x of 2, so we need to apply this process again. This time to find x of 2, this is equal to the first x of 1 plus f of x of 1 all over f prime of x of 1. So in our case, x of 2 is going to be 6 plus we got to go in and evaluate f of 6 and f prime. So let's look at f of 6. So I get 6 cubed, which is 216 minus 7 times 6 squared. So 7 times 36. So minus 252 plus 6 times 8, which is 48 minus 3. Which gives us back 9. And f prime of 6. So 3 times 6 squared, 3 times 36, which is 108, minus 14 times 6, which is 84, plus 8. Which gives you back 32. So if we go back in here and we plug in what we have x of 2 is equal to 6 plus 9 divided by 32. Which we could go in and we can reduce, so we could put that as a fraction. Well, not reduce, but we could put that in decimal form if we wanted to. So that goes 64, which would give us what, 6, 27, 26, I mean. Add a 0, so that would go in about, what? Maybe 8 times is too much. No, 8 works. Okay, so we could get an approximation and we could keep on doing this. This is where I was like, okay, sometimes the calculator we need to use in order to do these. The whole point in this was to be able to do these without calculators, but 32 goes into 80 is twice, so 64. Okay. So we get that this is approximately 6.2812. So what we were just finding was, oops, hold on, let me just check. I wrote down the wrong formula when I brought down this piece right here. This should have been a minus in between. This should have been a minus in between. This would have been a minus. I would have changed things around. So that's not a 6. Basically, I can think of it this way if I want. I can borrow 1 from here, make that a 5. So this would be 32 over 32. So this would be 5. 32 minus 9 gives us 23 over 32. Which is going to change our decimal. So I don't know, 32 goes into 230. Try 7. So 7, that's 14, that's 22. $32 goes into 60 once. 32 goes into 280. Eight times. Okay, so you can see that this is approximately 5.0718. Now let's go look at the graph of our original function, and let's look at where the graph is crossing the x-axis near when x of 0 is 5, and show that what we found was really close. So I'm going to pause the video while I pull up Desmos and put this into the calculator. So I plotted our function. You can see that where it's going across the x-axis, and if we look at this, it's going across the x-axis. 5.686. And we got about 5.718. So we got close, and we would have gotten closer the further that we went out. So this could get, like I said, really kind of tedious. The other thing is with this, and that you need to be careful with, is if you aren't given that guess and you choose something off, you might not ever get there. Like if you chose your x value to be maybe 0 in this case, and I looked at the tangent line, it wouldn't be crossing and it wouldn't be getting closer and closer to this x equals 5.6. So this is where actually being able to go in and define this in Desmos is really helpful. So let me go back to my original value right here. So let's look at our x of 1. So we can think of it as, how did I do this before? I don't remember how I did that. Let me think about it, and then we'll come back to it. So to get that value that we want to plug into Desmos, let's call it g of x. And g of x is going to be what number we're going to plug in, depending on what iteration we're looking at, of our original function f of x all over the derivative of f of x. So we're going to choose it to be g of x is x minus some f of x all over f prime of x. So let's go back in and plug in what we have for g of x for this problem in particular. So if I do that, I'm going to go back to my scientific calculator, and I'm going to define it. So I'm going to say g of x is equal to x minus, I'm going to put parentheses because I'm going to put, make a fraction. And I just wrote it down and I lost it. Maybe I didn't write it down. So x minus the original function, sorry, which is x cubed minus 7x squared plus 8x minus 3. Those are parentheses, divide by our derivative. And we found our derivative to be 3x squared minus 14x plus 8. Okay. So they told us to first look at g of 5, or plug in 5. And notice that we get 6, and that's what we got before, right? So now let's go down and let's look at g of 6. G of 6, I didn't go out as far, but we have 5.71875. I went out to the 8. We want to continue to do this until we start repeating itself. So we could even go further and find it closer to what that, where it's crossing the x-axis. So if I just copied what my answer is and plug in that answer into my function, I get 5.686, okay, which is getting closer to what we just saw when we graphed that. So if I take my answer and plug that back in, notice here, I have 5.686, and then I have 5.6857. So we're getting closer. So my math lab or your homework might ask you now to get find the root or 0 where it's crossing the x-axis within, to the nearest hundredths. And if that was the case, then we could stop because this hundredths position is repeating itself. If it wanted it to the nearest thousands, I would just go until my answer kept on going on. Oops. And so notice here, I even go out further. The decimals are going out the same until I hit, wow, I'm almost identical for a long time. So that's giving me a good estimate. And so using this program is really helpful when you're going to be doing your homework. I wouldn't give you problems like this where you would have to do this without a calculator on your test. So let's do one more example. So let's say you're given f of x is equal to x times cosine of x minus x squared. And they tell you to start with a guess of 1. So let's come up with what g of x would have to be so that we could just keep on doing this. So g of x I know is going to equal whatever I'm going to plug in minus f of x all over the derivative of f of x. So let's figure out what the derivative of f of x is. So I need to use my product rule. So that would be 1 times cosine of x plus the first x times the derivative of cosine of x, which is negative sine x, minus the derivative of x squared, which is 2x. So our g of x function is equal to x minus our original function of f of x, x cosine of x minus x squared, all over my derivative, which I'm going to write as cosine of x minus x sine of x minus 2x. So we want to make sure that our terms are in radians. So let's go in and we can look at what g of 0 is. Let's again pull up Desmos and let's just plug in what we have for g of x. Okay. I'm going to actually change the name because this is already knows what g of x is something else. So I'm going to call it h of x. So h of x is going to equal my x minus parentheses my original function, which was x cosine of x minus x squared, all divided by, oops, the derivative, which we found to be what was cosine of x minus x sine x minus 2x. Doesn't like something in here. And this could be where I need to be in radians. Maybe at times. I don't know why it's not liking my function.
You have cosine spelled wrong at the top.
Oh, that's why it's not. Thank you. Thank you, thank you. I didn't, my eyesight's going. Okay, so let's look at each that we were looking at and told us to look at one first. So we get 0.800. So let's look at evaluating at that answer. So now we get 0.74409. So now we're going to evaluate it at that answer. So notice we're getting closer. The tenths position is the same. So copy it, paste it. So 7.39. So we got up to the thousandths position is the same. So we can continue to do this. And it depends on how many iterations they want, or if they say continue on until you're to the nearest thousandths. And if that was the case, then we could stop here, but we can continue to do this. If we go up here, oops, and we looked at the graph of our original function, which was this numerator, and we looked at where it crossed the x-axis, we'll see that it's close to 0.739. So if I went up here and I graph this now, notice that one of the places that it's crossing is at 0.739, which we found to be the case when we use Newton's method. But just one thing to be aware of. So for instance, if you had maybe they give you an equation and not the function. So let's say they give you that 1/3 x cubed plus 1/2 x squared equals -3. And they wanted you to solve for this. We can basically use Newton's method by setting this equal to 0. If we did that, that would be 1/3 times x cubed plus 1/2 x squared plus 3 equals 0. So trying to find out where this is crossing the x-axis. We could choose f of x to be this function, as 1/3 x cubed plus 1/2 x squared plus 3. Now we can easily take the derivative, which would give us x squared plus x. And if we wanted to find where this was crossing the x-axis, then we would do some sort of a guess. And that's, again, where you need to be careful, because if you don't guess right, then it could be off. And so sometimes they're like, okay, well, go and graph it on the computer and get an estimate that way. Well, if we're going to graph it on the computer, then we can just figure out what the answer is, right? But we could graph this, or we could just start making a guess and seeing if that actually works out. So for instance, if I let my guess be x equals 0 for my first choice, we could go back in here and we could plug this in wherever we saw an x and f of x, sorry, into Desmos. I'm trying to do too many things at once. So if I did that, I go back to my function. G of x is equal to x minus my original function, which was this 1 divided by 3 x cubed plus 1/2 x squared plus 3, all divided by that derivative, which we found to be what? X squared plus x. Okay, so there's our function. We said, okay, let's look at g of 0. Let's see if this, well, g of 0 is undefined, so that's not going to work, right? So how about g of -1? Well, I'm not doing really good, am I? Has that been the case in the original? No. You can look at -3. Notice we get -2.75. So let's look at another number. Oops. So g of our answer is -2.71. So I guessed right. Well, not originally. If I plug in my next answer, I would get this. And now I'm exact. So when x is -2.75, that's where it's going to cross the x-axis. And we can always test that again by graphing our original function and showing that's what you get. So over here, -2.718, which we said. Okay. So that is Newton's method. And like I had mentioned at the beginning of class, we are now done with taking derivatives, and we're going to talk about now another major topic in calculus, which are antiderivatives and integration. So that's what we're going to be covering the rest of the semester.